Hello, dear learners. Welcome to the lecture on Unit 26 titled Process of Earthing and Soil Resistivity of Module 9 on Earthing of the MOOC's course on Electricity and Electrical Wiring. Earthing is the process of grounding an electrical system to the earth. This is typically done by installing a ground wire or electrode into the ground and connecting it to the electrical system. The purpose of earthing is to protect people and equipment from electrical hazards and to provide a safe path for electrical current to flow in the event of any fault. We have already discussed about the earthing and its requirement in the previous video. Here in this lecture, we will discuss about the process of earthing and the measurement of soil resistivity. The main objective of this lecture is to make you understand first the process of earthing, second the connection of soil resistivity with the process of earthing, and finally the method to calculate soil resistivity. So without further delay, let us start this lecture. There are several steps involved in the earthing process. Let me explain them one by one. First, proper selection of the location. So this is the first stage in building an effective earthing system, and one has to be sure that where you will install the earthing. This determination must be made using an electrical system's unique need, as well as an assessment of the soil type and other site factors. The most popular earthing system in civil engineering are plate earthing, pipe earthing, and rod earthing. So choosing the appropriate kind is critical for grounding system safety and reliability. Second point, proper installation. So once the location and type of earthing system has been identified, your next step is to find proper installation process. This typically begins with drilling a hole into the ground to facilitate the placement of the ground wire or electrode. It's essential to ensure that the ground wire or electrode is securely connected to the electrical system using appropriate connections. And you have to use proper clamps to establish effective grounding of the system. Three types of cable makes up the building electrical system: live, neutral, and earth. Each of these lines is critical to ensure the safe and effective operation of electrical devices within the building. The live wire is in charge of transmitting electric current from the power supply, and while the neutral wire serves as the current return channel to the electrical system. They work together to form a complete circuit that allows energy to flow and power a variety of appliances. The earth wire, on the other hand, is primarily intended to provide safety. It is attached to a buried metal plate which aids in grounding the electrical system. This connection allows excess electricity to dissipate to the ground, lowering the danger of electrical shocks and damage of devices in the event of short circuit. So earthing at home is often installed near the home's energy meter. This is where the grounding system linked to the electrical supply, which contribute to the circuit's overall safety and stability. Now the third point after installation that has to be kept in mind is testing of the earthing system. After installing the earthing system, it is critical to perform a complete test to guarantee that it functions properly and safely. So this testing procedure essentially consists of measuring the resistance of the earthing system with a specified instrument known as earth tester or ground resistant tester. To get reliable result, read and follow the manufacturer's instruction for the earth tester. And during testing, the equipment determines how well the earthing system conducts electricity into the ground. Resistance level should typically fall within an acceptable range of 1 to 10 ohms. If the resistance is less than 1 ohm, it suggests an extremely low resistance channel, which is generally preferred. However, if the resistance surpasses 10 ohms, it may indicate inadequate earthing quality. In such circumstances, additional study and corrective steps has to be taken, and you have to ensure that your system is working fine. So proper testing is required to verify compliances with safety requirement and protect both personnel and electrical equipments. Fourth and the last point, to maintain the earthing system. Earthing system actually require regular maintenance to ensure that they continue to function properly. This may involve inspection of the ground wire or electrodes for sign of corrosion or damage. So in such situation, you may have to replace it if necessary. It's also important to periodically test the earthing system to ensure that it is functioning properly. Overall, the earthing process consists of establishing the location, the type of earthing system, and then installing, testing, and maintaining it. By taking these actions, you can be sure that your system is working perfectly and you are sort of out of danger in any electrical hazard. So different types of earth are used to link the metallic part of electrical appliances or installations to the earth to prevent any risk associated with it. So now we'll discuss the different types of earthing in a separate video. Here in this lecture, our primary goal is to discuss the procedure of soil resistivity and how to calculate soil resistivity. So we'll discuss that in the next part of the video. The basic objective of earthing electrical system is to establish a single reference. To attain this goal, a low resistance connection to earth is always recommended. However, this is frequently difficult to attain this, and it requires knowledge of varieties of conditions. For example, first, soil resistivity. Second, stratification. Third, size and type of electrode used, and hence the depth to which the electrode is buried. Fourth, presence of moisture and chemicals at the site. As moisture content increases, resistance may rapidly decrease. So resistance versus resistivity. These two terms will be used very much in this video. So what is the difference between them? Let's start by discussing the difference between resistance and resistivity. Resistance refers to how much a material opposes the flow of electric current and is typically measured in ohms. In contrast, resistivity is a material specific property that quantifies how strongly a material opposes electric current. The unit of resistivity is ohms meter. Resistivity is an intrinsic property of a material, meaning it doesn't depend on the material's size or shape. It indicates how much the material resists electric current per unit length per area. However, the resistance of a material depends on its shape and size. So in summary, resistivity is calculated based on resistance, the length and the cross-sectional area of the material. Meanwhile, resistivity is a fundamental characteristic determined by the electronic structure of the material, and it is also influenced by temperature. Resistivity is often used to classify materials as conductors, semiconductors, or insulators based on their resistivity ranges. On the other hand, resistance is a practical measure used in designing and analyzing electrical circuits. When analyzing a circuit, it is crucial to ensure that the components operate safely under specific electrical current. For example, copper and aluminum have low resistivity, making them good conductors, while other materials like rubber have high resistivity and hence called insulators. Therefore, when resistivity is high, the material offers high resistance to electric current. Additionally, resistivity generally increases with temperature in conductors. Now, to understand mathematically, consider a simple electric circuit as shown in the figure. According to Ohm's law, as we have already discussed about Ohm's law in the previous video, that the current flowing through a wire is directly proportional to the applied potential difference across the two ends of the wire. This relationship is V is equal to current times resistance, where V is the potential difference across the wire, I is the current passing through the wire due to P, and R is the resistance offered by the wire while to the current. So from this formula, we can see that the resistance R is equal to V by I. Thus, resistance is inversely proportional to the current flowing through the circuit. When resistance is low, the amount of current flowing through the circuit is high, and vice versa. Now the formula for resistivity is resistivity rho equal to R times L divided by A. So when I say like that, here you have seen that R is your resistance of the wire, L is the length of the wire, and A is the area of cross section of the wire. So when we talk about soil resistivity, it basically measures the resistance between opposite sides of a 1 meter cube of soil. Why is it vital to measure soil resistivity when installing earthing? So that's a very important question to be asked. Soil resistivity plays a vital role in the design and implementation of earthing system, as it directly influences the resistance encountered by the grounding electrodes. A thorough understanding of soil resistivity at a given location, along with the variety factors such as moisture levels, temperature fluctuation, and depth, is very essential for proper installation of a grounding system. This knowledge not only aid in achieving the targeted earth resistance value, but also ensures that this is accomplished efficiently and cost effectively, minimizing both time and resource invested in the process. By effectively assessing these parameters, engineers can create more reliable and safe grounding system that performs optimally under varieties of environmental conditions. Now, question is how to test soil resistivity. So, earthing system situated near the Earth's surface requires correct modeling of the top soil layer, which experience highest current densities. Here in this lecture, we'll focus on two popular methods to measure soil resistivity: Warner's array method and Schlumberger's array method. Here in this lecture, we'll discuss about Warner's array method, which is also known as the 4-electrode method, in details. We'll also do a comparative study between Warner's method and Schlumberger's method. Also, we'll discuss about the merits and demerits of this method in this lecture. So, let's go to Warner's array method. One of the most time-consuming method for carrying out transverse in soil resistivity measurements is the Warner's array approach. To effectively do this task in an acceptable amount of time, a team of up to 4 people is actually needed. Because of its advantageous ratio of received voltage to transmission current, the Warner's approach is currently the recommended option for earthing design, despite its many challenges. Because of these features, it is among the most accurate techniques for determining soil resistivity at a deeper depth. Here in this picture, you can see the diagram for Warner's array method, which is also known as 4 electrodes method. There are 4 electrodes used in this process, and equipment needed in this process are 4 electrodes, voltmeter, ammeter, and resistivity measuring instrument. So in the figure, one can see how resistivity is measured using measuring tools. First, at regular intervals, 4 electrodes are placed into the ground to a particular depth equal to 1/3 of their total length from the surface. The inner probes, called potential electrodes P1 and P2, are positioned closer together, while the outer probes, known as current electrodes called C1 and C2, are set further apart. So this configuration is vital for accurately measuring soil resistivity with an earth resistant tester. To initiate the measurement, connect the electrodes to the earth resistant tester, making sure that connections are secure. After everything is properly set up, take the initial resistance reading, which will provide valuable information about the soil conductivity. Following this, adjust the position of the electrodes by moving them away from current electrode C1 by the same interval as their initial placement. As you do this, ensure to insert the probes deeper into the soil to keep the measurements depth accurate. Next, keep relocating the electrodes further from C1 and adjusting their depth, while consistently logging the resistance values at different depths and distances. This information is essential for understanding how soil resistivity varies with depth and distances. To calculate the soil resistivity, the formula used is rho equal to 2 pi A R, where R represents the resistance in ohms measured between the electrodes. A indicates the distance separating the electrodes measured in centimeters. Now let us derive the above formula. But before deriving the formula for resistivity, at this stage you should be able to answer the following questions. So let's now complete the derivation of the soil resistivity, and let's see how we can arrive the desired formula. The potential at a distance r from any point current source is actually given by V equal to rho I 2 pi r. So r is the distance. Now here rho is the resistivity, I is the current flowing through the current source. And now to derive the formula, first we have to consider the relationship between electric field and the current density, which is actually given by E equal to rho J, where J is the current density and rho is the resistivity. Current density, what is the definition of current density? So current density is defined as the current per unit flowing through per unit area. Here in this case, as the current spreads spherically once it enters the earth through the electrode. So J is hence given by J is equal to current per unit area. So here in this case it will be 2 pi r square. Now why it is 2 pi r square? Let's understand that thing. To understand that thing, we have to draw one diagram. So let's draw the required diagram. Okay, so consider that this is the ground. Okay, so this is the ground and I am considering single electrodes. So this is my single electrode. Okay, so current I will be flowing through this electrode, and so when it enters, so we want to calculate the potential at some point P here because of the current flowing through this wire, that is I. Okay, so now as I said, so when current enters in this region, so it will enter spherically. Okay, so we have to consider some concept of electricity and magnetism here. Okay, so but as you see, when it enters spherically, so you can assume that it is spreading like that, a sphere of radius r. Okay, so in that way. So in that case, it is a hemisphere, right? So it's a part of this particular sphere, but it's a hemisphere. So what is the area of this hemisphere? So if r is the radius, then it should be 2 pi r square. Hence my current J is given by I by A, that is I by 2 pi r square. Now we know from our basic knowledge of electric field that the field inside a spherical conducting sphere is 0, and at any point outside the sphere the field is due to the sphere is equal to that of a point charge sitting at the center of the sphere. Hence the potential inside such a sphere is constant, and outside the sphere it is equal to that of a point charge at the center if the test charge or unit positive charge is brought from the infinity. Obviously, if the charge Q is uniformly distributed throughout the sphere, solid sphere, then the situation will be different. Anyways, so in this case, electric field is given by, so I'll put this value of J here in this equation. So it will be, this is electric field at some point P. So this is my position vector, so at point P, so R. Now, what is the relation of electric field with potential at that particular point? So we know that the formula is given by E is equal to rho J is equal to minus del V by del R. Del V by del R. Okay. So now electric potential can be calculated. So what you can do is that you can take minus dV is equal to E dr. Okay, hence integrating, so what will you get is that, so when you will do the integration from 0 to V dV, and it is equal to minus integration. Okay, so my initial position is from infinity to the point R. So it is E dr. Okay, so E dr. So this is the value of E now. So what I can do here is that, so I'll put this thing together. So let me put this thing together. So now let's put these things here. So this is minus infinity to, sorry again, infinity to R. E is my, what was my, so E is my rho. Rho is constant, it is not depend, rho is constant because it is not depending on R. So I can take rho and I outside of the integration, and what will be inside, it is 2 pi R square dr. Okay, so after completing this integration, what will I get? So I'll get, so from here I'll come here, so I'll get that V is equal to, from this calculation, this minus sign, when we'll put the limit, lower limit and upper limit, so finally the result that will come is rho I by 2 pi R. So this is the formula, desired formula for potential because of the current source. So here from this relation we have seen that the potential at any point due to the inward current in the electrodes depends on the current and the current and the resistivity, and it is inversely proportional with the distance. So that means as far as we go away from the electrode, my potential is decreasing. So that is another important point. So near the electrodes the potential is high, and when you go away it decreases. So now the setup that we have considered earlier is a single electron setup, through which we have just shown that how to calculate this formula. Now we will consider the two electrode setup for, let's say, so the condition will be, okay, so now what the scenario should be, so this is my ground, okay, so let's say this is my ground. Now I have one electrode, so this is your C1 electrode, okay, this is your C1, and another electrode, this is your C2, this is your C2. So current is entering here and they are connected, so current is leaving the earth here, sorry, it is I, same current, okay, so current entering to the ground through this C1 and going away from the ground through C2. So now our aim is to calculate potential at some point here because of this current and this current, right? So let's say I call it my R1 and my R2, and this is my point P where we want to calculate the potential. So what will be the potential at this point P? It will be just the sum of the potential because of this current and this current. But the important point to note is that current has an opposite direction. Here it is inward, it is outward. So final V total, so if you calculate, so it will be rho I by 2 pi R1, right? And since the other current is going opposite direction, so it is rho I by 2 pi R2, right? So you can take this constant part, rho I 2 pi, it will be 1 by R1 minus 1 by R2. So this is the potential at point P because of these two current carrying electrodes C1 and C2. Now you have to remember that in Werner's method we not only have two electrodes but we have four electrodes. So there are two electrodes sitting at the center, and we have to consider that also. So if we consider that, what will we get? So let me clear this thing. So image will be something like, so you have one electrode. So what you know is that, so current is coming coming inside, inward to the ground through C1 and going away through C2. You have already calculated potential somewhere here because of this and this, okay. So now we have to I'll say that this distance is my R1, this distance is my R2, and this distance is R3, okay. So now we want to calculate potential, say at this point and at this point, because of, so at this point the potential will be because of this current and at a distance R1, and because of this current at a distance R2 plus R3. Similarly, at this point, potential at this point will be because of this current at a distance R3 and because of this current at a distance R1 plus R3. So you know that total, how to calculate total potential because of these two currents. We have already derived that formula, right? So now I'll just write so that potential at this point is V2 and at this point it is V3. Okay, so my V2, what will be V2? So it is, as I said, it is rho I by 2 pi. So recall the formula that we have already got. So it is, because of this current, it is 1 by R1 at this point, and because of this current, so this is at a distance R2 plus R3, so it is R2 plus R3. Fine. Now V3 similarly can be rho I 2 pi. So now you see the distance, and from here you can say that it is 1 by R1 plus R2 minus 1 by R3. Right. So what is V23? What is the potential difference between these two? What is the potential difference between these two electrodes, potential electrodes, that is V23, right, which is V2 minus V3. Okay, so if you subtract that, so you'll get the formula, get the answer, right? Now another important point is that in Werner's method, these separations are of equal distance. That means your R1, R2, R1 equal to R2 equal to R3, and I'll call it, say, R. Okay, so in such situation, so what would be your V23? So you can just put the value of V2 here, V3 here, and calculate the difference between them. You will get V23, and in that case you subtract this condition, put that condition, and what you will get is that your V23 is nothing but, it is equal to rho I by 2 pi R. Okay, so if your R is nothing but, if it is A, R is equal to A, just replace this R by A and you get your desired result. Okay, so from here, so V23 is the potential difference between the potential electrode P2 and P3. Okay, so if I write V23, that is my potential as V. Okay, so V is equal to rho I, right, rho I 2 pi small r. Okay, I'll take it this side to get the resistivity. So what will be my resistivity? So here, from here, resistivity is 2 pi r V by I. Okay, so from Ohm's law, what do you know? V by I is nothing but the resistance. So that means this is your desired formula of resistivity. Okay, so this is the desired formula for resistivity. Now for comparative purpose, we will quickly go through Schlumberger's array method. In this method, like the previous one, we still have 4 electrodes and the 2 outer electrodes are still carrying current. But the separation among the 4 electrodes in this time is not same. Outer electrodes are also called source electrodes, while the inner electrodes, also known as receiver electrodes. The formula to measure the soil resistivity by this method is shown here in this slide. With a tiny distance between them, usually no more than 1/5 of the distance between the current electrodes, the potential electrodes are arranged strategically in the middle of the electrode array. The precision of the measurements taken during the survey depends on the configuration. The current electrodes are gradually separated to increase the separation as the survey goes on. But the potential electrodes stay fixed in place. So this is another difference. The procedure is repeated until the measured voltage drops at a level too low for precise measurement. Particularly for groundwater exploration applications, and aggregate mineral resource assessment, this method is widely used. It also used in vertical electrical sounding. This approach has a number of advantages over Werner's method. In Werner's method, it can be labor intensive and time consuming to relocate all 4 electrodes at a time. But here, since 2 electrons are fixed, potential electrons are fixed at their position, so we need less labor, hence less human, to move the current electrons during measurements. Additionally, this method offers more versatility for investigating subsurfaces resistivity at different depths. Practitioners may easily adjust the depth of measurement without having to completely reconfiguration of the electrodes array by changing the space between the current electrodes. Consequently, this technique is highly favored for precise determination of soil resistivity at various depths. Now, there are some precautions to be taken while measuring soil resistivity. First, one has to make sure that the electrodes and resistivity meter are suitable for the particular type of soil being analyzed and are operating correctly. Second, to guarantee accurate reading, use the Schlumberger's method with appropriate spacing and the Werner's method with consistent spacing. Third, to avoid excessive contact resistance, make sure the electrodes are firmly planted in the ground. Fourth point, severe weather conditions such as rainy season or dry season can significantly affect the soil resistivity. Hence, one should avoid taking measurements in such time. Another important point is soil moisture. It can vary greatly over time and one should be aware of that, and while taking measurements you should be notice that soil measurement content is at a level that is normal for the use. Another important precaution is that while taking the measurement, there should not be very heavy power system, electrical power system near the measurements. So it may hamper the readings. Next, to avoid faulty readings, place the measurement apparatus away from electromagnetic interference sources such as power lines, transformers, and communication devices. Additionally, keep in mind that temperature might affect soil resistivity. Take measurements at a constant temperature wherever possible, or account for temperature changes in your computation. Now, we want to conclude this video. I hope after going through this video, we have learned in details how earthing is done. In addition to that, it should also brush up your understanding of resistance and resistivity and their connection. We should now be able to explain Werner's array method in details and hence should be able to calculate soil resistivity for such setup. I hope now you will be able to answer the following questions. Dear learners, I hope the information provided in this video helps you deepen your understanding of earthing process and soil resistivity. See you with a new video on the types of earthing and their advantages and disadvantages in the next lecture. Thank you.